All right, now that's on the quantitative, the cycle, the full component of quantitative health assessment. Now we'll go over each component one by one. We start with hazard identifications. So in hazard identification, what we are trying to do here, we want to identify, the overall goal is to identify contaminant of concern. So what we want to do in hazard waste is we want to know what chemicals is over there and how much of them, their concentration in soil, air, or whichever place of water, whichever media you want. And where are they, how they distributed spatially, and finally we want to know how they move in the spatially, and to see if they can be released from a site to environmental, to other places of concern where they can get in contact with people. Now that's on the hazard identification. So on hazard identification, the main purpose is just trying to find out more information about the chemicals of concern. But in the United States, many of this hazard identification was taken care of by the laws, because there are millions of different chemicals. What you're going to do, and the laws, actually environmental laws, usually in the United States give you a very detailed list of different chemicals that should be concerned, and you can based upon these chemicals and based on the list different laws, you can actually do corresponding actions to find out where these chemicals are, because these chemicals are those of biggest concerns. So when it comes to, we mentioned this previously. So in water, we were talking about the main purpose, the big one is Safe Drinking Water Act and Clean Water Act. So the chemicals of concern listed in this, and they have this maximum contamination level, MCLs. This was calculated based on health risks. And basically, they collect a lot of data from many different places and identify those biggest chemicals that has the biggest health impacts, compile this in there. Now this for the primary, which is used for protecting human health. And they also have a secondary levels. The secondary levels normally, it's slightly not as strict as the primary levels, and used to protect how it looks like. That's in water. But in air, we also mentioned the biggest one, the Clean Air Act, CAA, and a bunch of CAA amendment. It also has two standards, primary and secondary. Primary standard is trying to protect humans, and we have secondary standard protect animal and welfare, environmental welfares. And this standard for different chemicals will have very detailed list there. We mentioned this. The biggest one of concerns in air is NOx, the 6 NOx. Carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, PM2.5, PM10, and lead. Now those concentrations are set in NAAQS, National Ambient Air Quality Standard. Their concentration level was set in there. You cannot exceed them. If you do, you have to do something about it, because state implementation plan, the entire state, and actually the surrounding state will have to come together to do something about it. If you want to meet a large quantity of these chemicals, from a new source, you have to go through this new source performance standard, NSPS, very stringent test to protect the concentration level, just protect human health there. In addition to NAAQS, the 6 criteria for pollutant, we also have 180 air toxics. A lot of them are VOCs, like benzene, but not all of them are VOCs. Asbestos, not really VOC, right? So now they have the emission standard. They don't have a concentration standard. Depends on where you are. Not really depends on where you are, but you cannot exceed the certain amount per year, certain tons limit. If you do, there are going to be some consequences that are not regulated based on concentration in the air, rather that regulated based on emissions. We talk about NES-HAPS, not National Emission Standard of hazardous air pollutants. Now, we also, when it comes to the solid waste, we have, we mentioned this before. There are 4 characteristics for hazardous waste: toxic, ignitable, reactive, corrosive. It's four most important characteristics of hazardous waste. And their regulations is RCRA and the CERCLA. We mentioned this. RCRA is based on Hazardous and Solid Waste Amendment. Their HSWA substantially actually amended RCRA. It's one of the most significant amendment to RCRA. And we also have CERCLA is a cradle to. Never mind, can't pronounce that. So CERCLA is a Superfund. It's a Superfund Act. So initially it was, we mentioned, it has 1.6 billion fund to clean up the most toxic contaminated site. It's a historical site in the United States. But later the Congress found this not remotely enough. So they increased to 8.5 billion through SARA, one of the amendment. In the whole United States, there are 1,000 sites, national priority site, national priority list, and this is just a quick map, and a lot of them are, of course, clustered on the northeastern United States. Many of them are still under remediation. It takes a long time to do that. Now that's on hazardous identification. Quick thing on the compatibility, hazardous waste compatibility chart. Now this chart pop up in one of the FE exams. So if you want to learn more about this chart, I would strongly recommend you read this book report. It's not that long actually. The biggest part is actually appendices, but this one is only dozen pages long to give you more detailed information. So now what this means is first, as you notice that you have this different code, right, from number 1 and all the way to number 107. But they're disconnected. From number 1 to number 34, then there's no 35, then you end up having a 101 to 107. So what happened is this was originally published in 1980. So what happened is this chart, the main purpose is trying to determine if two hazardous waste is compatible, if you can mix them together. Because there's so many of them, you need to have a guidance on whether you can dispose the different hazardous waste together, right? So now in this report, they developed this generalized method. Generalized, you cannot, say, okay, it looks compatible from this, it has to be compatible. No, it's not true. It's just a general guidance for further details, for the exact reaction, what will happen. You have to rely on your chemistry information, chemistry education, but this is just for general guidance. How you use this is that first, say you have two chemicals, you want to know if you can mix them, right? So in this report, in appendices 1, if you look up that chemical, it will tell you which group it is. If it's under 100, from 1 to 30 something, it was this group number was categorized by the molecular structures, as by functional group and rather their structures. But from 101 to 107, it's not on structures. It's generalized chemical reactivity. That's why they started from new number. They don't want to confuse you because it's not ranked based on their structures. See, now you look up appendices 1 on this document, and you find which group this chemical is. 2 of the chemicals, right? You want to mix 2 of them. Then you look up another one, found which chemical it is. You would have 2 groups, right? If it's 1 group, of course you can mix them. And you're mixing the same thing, so there should not be a problem. But also depends if you combine other things like that. We mentioned the milk. If you combine milk together with water, that's going to be an issue. Anyhow, so normally, if you have 2 chemicals, you mix them together, exactly the same chemical, you mix them, there shouldn't be an issue. But say you have 2 chemicals, and say you have one chemical is 4, the other chemical is 5, then you look at 5, 4, just look at their intersections. You find this teeny cube here. Then when you find this cube, you check what's the number in there. What's the alphabet in there. Then now this code you can look up in this table. Heat, fire, gas, toxic gas, flammable gas, explosion, polymerization, solution toxic materials, all unknown. So you look up the code in the corresponding grid and find out what does it mean. Now this tells you what could happen if you mix these two chemicals together. So the biggest one is 107. It's basically water reactive chemical. You don't mix it with anything. It's very toxic. Another toxic is very hazardous. It's throw them in there like pure sodium. You throw them in there, it's going to explode. Throw them in water, it's going to explode. Now this is on this compatibility chart. Essentially, what this chart trying to give you is a generalized idea of whether you can mix two chemicals together or not. It's based on 1980. Many more chemicals popped out. Many, substantially technical advancement occurred since 1980. So generalized guidance, don't rely on it. If you see something, if you see nothing here, it doesn't mean it's nothing. It's just a generalized guidance tell you this. Okay, now that's all on hazard identification. It's the first step of quantitative health risk assessment. The main idea is hazard identification is trying to find out the chemicals of most biggest concerns and identify where they are, how much they are, where they are, how much they are, and identify whether they will move and get in contact with people, do some damage, right? It's on the first step, identify those chemicals. Second step is exposure assessment. Now, what this step in do here is how much the chemicals get in contact with people, to trigger health issues, potential health issues. For a chemical to get in contact with people, first, of course, you need to have a source. Then you need to identify the fate, how chemicals move around in the environment. Through a transport, either in air, water, or maybe underground water, and finally get in contact with people, you have a dose. Now, in classical toxicology, everything is toxic. You drink too much water, you die. You drink a ton of water at the same time, you die. It's just everything is toxic. Everything, the most important thing is dose. So how much you injected determine how toxic it is. Even say the cyanide. If you drink teeny at the nanogram level, you'll probably be fine, right? Like radioactive materials, we mentioned Hanford-site. Hanford-site, they have radioactive material leak every year. Every year. I mean, that's guaranteed leak, but it totally depends on how much they are. If they only leak teeny amount, it's really not a big concern. So dose is important. When you, maybe a kind of related notes, if you hear something, in the media often trying to exaggerate, give you some big, big news, but please remember dose is really important. Sometimes they exaggerate the toxicity of certain component, but if they're teeny amount, it's really not an issue. Also, when exposure assessment, one thing to note is they do have bioconcentration BCF, because a lot of chemicals, especially organic chemicals, that turned to have bioaccumulation, cascade up the food chain, the enrichment up the food chain. So totally depends, but I just want to put this here, but we're not going to be talking about this. There's no calculation related to this. Okay, now one of the important things in exposure assessment is CDI, chronic daily intake. So CDI, the equation here is C, which is the concentration, times the contact rate or intake rate, and then times exposure frequency or exposure time, duration, and divided by body weight and averaging time. Essentially, what this is, just ignore this equation at this moment. Essentially, the chronic daily intake CDI, what it's trying to calculate is how much pollutant, how much chemical get inside your body, and per amount of your body weight, and per certain time. So The reason why you have body weight is because, some, like for example, children, they have lower body weight, but especially at risk. So essentially, you can ignore all the equations. The idea is the chemical gets inside you, divided by your body weight, and divided by the time, right? So because there's so many different routes, see, you have a thermal, some chemicals, we mentioned mass of mercury. If you have mass of mercury and on your skin, they will get inside you. There will be a trace amount get inside you, and they can be really toxic. You inhale air toxics, you drink water, there's some toxics in the water get inside you, and it's just, there are so many different routes, right? But different routes, the calculation is, if you read a bunch of books, the calculation, there are many different equations, but the idea is exactly the same. How much chemical gets inside you, and divided by per your mass, body mass, and per time. Okay, to calculate this, what you need to have is, of course, concentrations, and how much the mixture of toxic and other stuff get inside you, and also you need body weight. Also, you need averaging time, right? So to do this, you have to assume a bunch of things because people have different routes. Different people have different inhalation and intake dose. But this is just some parameters. For example, normally adult drink 2.3 liters per day. For kid, 1.5. Air, normally adult male inhale 15.2 cubic meters. Adult female, 11.3. But kids, 8.3 cubic meters per day. Now these are body weight assumptions, averaging time. Of course, you don't even have to know this, but average life expectancy, we say 75 years. And exposure, that's EFD, exposure time, exposure frequency. So we'll discuss a bit more on next examples. And if you read the book, it's slightly different from the book, which is the table 14-7. It's slightly different, but the idea is the same. I would use this, but if you want to use the parameters in table 14-7, fine. It's okay, whichever you choose. And you might choose this weight towards interest because it's the United States, right? Anyhow, so just an example. So now this was trying to calculate 1,1,1 trichloroethane. It's kind of like significant concerns. So calculate chronic daily input of 1,1,1 trichloroethane from exposure CD, which contains the concentration 0.2 micrograms per liter. That's the concentration 1,1,1 trichloroethane in the water. And assume the individual is 80 years child, consuming water at child rate, which is the child, assume his weight 33 kilograms, and drink 1.5 liters of water per day. Now, if the child drinks 1.5 liters per day, you know the concentration is 0.2 micrograms per liter, and so naturally the total 1,1,1 total amount 1,1,1 trichloroethane get inside the child is 0.2 microgram per liter times 1.5 liters per day. Now, it's asking for 5 years. So now this is just 1 day, right? Now you times 365 day per year. If you argue it could be 366, fine, you plug in there. 5 years divided by the time, that weight, and averaging time is per day. So you have 5 years, 365 days per year, end up with this number. Now this is the about 0.0091 microgram per kilogram per day. Now this is chronic daily input for this child, 80 years old child, for the chronic daily input of 1,1,1 trichloroethane from ingestion. Idea is amount of chemicals get inside the child, which is water she drinks, concentration in the water, days, and then divided by by the mass, body mass, and by the time you are looking for. This is daily chronic input. So the second is that, say, assume this individual is an adult female, and take short baths every day, about 10 minutes short baths. Assume the average air concentration is 2 micrograms per cubic meter. 10 minutes shower every day, concentration is 2, and breezes is 11.3 cubic meters per day. If we ignore everything else, so what we have is this, interest in the inhalation dose of CDI, of 1-on-1 trichloroethane. Now, every day, this female breathes in 11.3 cubic meters. But we are only interested in the 10 minutes she's taking the shower, right? So what we are looking at is 0.447 meters per cubic meter per hour, but only 0.17 hours per day. That is our interest. So you times it together, which give you how many cubic meter that this lady inhales that contains this amount of the chemicals of interest, right? Now you have the concentrations times the cubic meters she breathes while taking showers. Again, she takes shower every single day, so you have 5 years every single day, and divided by, this should be a different weight. Then times this, I'll put the revised version, that should be a different weight, and divided by the 5 year and the 365 days per year. Now, same idea, how much chemical get inside human body? The chemicals only get in contact with humans during the bath, and that's certain amount of air. We only care about the amount of air that's she inhaled during the bath, right? That's 10 minutes. Now, this the number is really small. The total CDI is going to be the same. So, but if you do the calculation of detailed exposure calculation, sometimes you encounter a situation where it's not every day, maybe every work day, every Monday, thing like that. In this case, now these numbers would be different because you're only interested in those days that she or he is exposed. But these numbers below here would be the same because you're averaging over an entire time period. So now that's on the example of a chronic daily input.